When we draw the conformation of alkanes, we care about two types of strains, torsional strain and steric strain. This is for alkanes, and we show those in the numeric projection when we are drawing the staggered conformations and the eclipse conformation. Now, as for the conformation of cycloalkanes, so if you have an alkane in a cycle and you want to draw its conformation now, cycloalkanes still have torsional strain and they have steric strain. But there's an additional type of strain that they have, which is called the angle strain. Now, angle strain is a strain when the bond angle is deviated from the 109.5, whether it's less than 109.5 or more than 109.5. Let's have an example. There are different types of cycloalkanes, ranging from a cycle of three-membered rings to a cycle of six-membered rings in there. Each one of these carbons of the cycloalkane has an sp3 hybridization. So each one of those is an sp3 hybridization, and we know that an sp3 hybridization should have a bond angle of 109.5. This is the ideal bond angle. So for every one of those carbons that constitute these cycles, the ideal bond angle is the 109.5. However, you can see that if I want to arrange the three carbons in a cycle, then I need to compress the bonds to 60 instead of 109.5. So this is a deviation of 49 degrees. This deviation here causes what we call an angle strain. It's the energy due to the compression of the bonds. Same thing for the cyclobutane. The angle is 90 instead of 109.5, so it's a deviation of 19. For the cyclopentane, it's a deviation of 1 degrees, but for the cyclohexane, it's actually an expansion of 11 degrees. Because of the angle strain, the bond angle in cyclopropane is the least among all the cycles. Compared to other cycles, cyclopropane is the most strained of all the rings, meaning that it does have a very high energy. The reason for its energy is because all its carbons, they lie in the same plane. This is the only way to draw cyclopropane, showing all the carbons in the same plane. Each one of these carbons is an sp3 hybridization. And those carbons being in the same plane, they will produce a lot of angle strain because the bond angle in this case is deviated from the ideal bond angle, which is the 109.5. In addition to the angle strain, you do have torsional strain. Torsional strain is due to the eclipsing of the bonds. Now, these are the bonds that are eclipsed. In this case, actually, all of those, they are eclipsed in there. If you look at along this line and you want to draw a Newman projection between those two carbons, you can easily see how the hydrogens are eclipsed. Eclipsing of the hydrogen causes torsional strain. So cyclopropane has a lot of energy, and that energy due to the angle strain and the torsional strain. Now, another important thing about cyclopropane is its bonds, its sigma bonds. These sigma bonds are very weak bonds. Now we know that a sigma bond is the overlap of two sp3 hybrid orbitals. So I have an sp3 hybrid orbital here, and I have an sp3 hybrid orbital there. So these two hybrid orbitals, each one has one electron, and they overlap and they make the sigma bond. Because the bonds are squished, the orbitals are not linear. So the orbitals have an angle in this case. Because the overlap is not linear, that makes the sigma bonds bent bonds. And because they are bent bonds, these bonds, they are very easy to break. They are very easy to break, and that makes cyclopropane very reactive. Cyclobutane has one more carbon than cyclopropane. And whenever we want to draw it in naming, we draw it as a planar structure showing all the carbons they lie in the same plane. Now there's a problem with this drawing because this drawing has a lot of torsional strain. If you want to draw the Newman projection along these two carbons, while all the carbons lie in the same plane, you will have eclipsing of the bonds here. So in order to release the energy of the structure, make it less. What we do is we represent the cyclobutane in the form of a puckered conformation. Puckered conformation is when you take one carbon from the cycle and you point it outside the plane. Something like this. To express that or to draw it on paper, you draw three carbons because cyclobutane is four carbons. So draw the three carbons and draw one carbon in the center and then connect the carbons together. In this case, I took this carbon and pointed it out of the plane. This is the molecular model for it over here. So now if you draw the Newman projection, you're going to see that the hydrogens are not quite eclipsed. So that is going to decrease the torsional strain. You're not going to have too much eclipsing of the bonds in there, less energy. So this is a more stable representation of cyclobutane than showing all the carbons belonging to the same plane. We're going to do the same thing for cyclopentane. So on paper, cyclopentane, we represent it as a cycle of five-membered rings, five carbons in there. And the five carbons, the way that we are drawing it, it seems like they lie in the same plane. So this, again, has a lot of energy, a lot of torsional strain. So to decrease the torsional strain, we're going to take one carbon and point it out of the plane as we did for the cyclobutane. So it's going to look like this. So whenever I ask you a question about stability, it's better to represent the cycle in a puckered conformation rather than representing it in a planar conformation. This is more stable because it has less torsional strain. This means it has less energy. Definitely the angle strain is there. But the angle strain compared to cyclopropane is way less because here now the bond angle is 120 degrees. In cyclopropane, the bond angle was 60. Cyclohexane is a cycle of six carbons. So whenever we want to show cyclohexane on paper, when we are working with naming, we draw cyclohexane as a planar structure, showing all of its six carbons, they lie in the same plane. This again has a very high energy. In reality, cyclohexane does not exist as a planar structure. It is not planar because of the torsional strain. So to decrease the torsional strain, we're going to do exactly as we did for the cyclobutane and the cyclopentane. But now here, we are going to express the cyclohexane in a form of a chair conformation. So with the chair conformation, normally we have three carbons pointing up, three carbons pointing down. This carbon is pointing up. This carbon is pointing up over here, and this carbon is pointing up there. This is the molecular model for cyclohexane. And then we have the three carbons that are pointing down. This carbon is down, this carbon is down, and this carbon is down. To know that the carbons, if they are up or down, just to trace the direction of the bond. And if the direction of the bond is pointing upwards, then the carbon is going to be up. If it's pointing downwards, then the carbon is going to be down. We name it as a chair because it looks like a chair. And this is a puckered conformation. So here we're taking the three carbons and we are pointing them out of the plane, and the three carbons, we are pointing them behind the plane. So let's go ahead and see how to draw the chair conformation. Looking at the cyclohexane, cyclohexane has 12 hydrogens. Its molecular formula is C6H12. It does have a DBE of 1, and it follows the molecular formula of CnH2n because it is a cycloalkanes. And the cycloalkane has a formula of CnH2n, similar to alkenes, because alkenes have a DBE of 1, cycloalkanes have a DBE of 1. So both they carry the same molecular formula. Let's start by drawing the chair conformation. So when you want to draw the chair conformation, it needs some practice, but at the beginning, this is how you do it. You draw two lines, two parallel lines. One of the lines is longer, slightly longer than the other. And then you draw one point up and one point down. This point is represented by a carbon. After all, we have 6 carbons that we are going to connect together. So you're going to connect. So the end of the lines are going to be carbons in this case, and you're going to go ahead and connect the carbons together like that. So this is going to be your chair conformation in here. As we can see, every single carbon has 2 hydrogens. So we want to represent them in the chair conformation. To represent them in the chair conformation, their position is going to be axial and equatorial. So there are 2 terms that we are going to introduce. Axials, or 2 positions where the hydrogens are going to be. On the axial position and on the equatorial position. Now, the axial position is abbreviated by an A, and the equatorial position is abbreviated by an E. The axial line is a line that follows the direction of the carbon, and normally it is a perpendicular line. So it's going to be either up or down based on the direction of the carbon. So let's go ahead and draw the axials first in here. And this is how you do it. You draw your axials first, and then you draw your equatorials. So to draw the axial, as I said, we're going to follow the direction of the line. So, or the direction of the carbon. So this carbon is pointing up or upward because the lines are pointing upwards. So this carbon is an up carbon, so its axial is going to be up. Okay? Now, this carbon here is pointing down because its lines are pointing down. So this is why the axial is going to be down. It is a straight line, so please draw it as a straight line because it is a perpendicular line. You start drawing your axials first, and then you draw your equatorials. This carbon over here is pointing up because the lines that are coming to this carbon, they are up. So this is why the axial is going to be up. It's not a tilted line, it is a straight line, perpendicular line. This one is down, this one is up, and this one is down. After all, you're going to end up having 3 lines that are up and 3 lines that are down. So you're going to have 3 axials that are up because you have 3 carbons that are up. And then you're going to have 3 axials that are down. So this is an axial that is down, this is a down, and this is a down axial in there. Okay? After finishing drawing your axials in there, go ahead and put your hydrogens. So the hydrogens here are on the axial position. I'm drawing here a non-substituted cyclohexane. So far I've drawn 6 of the hydrogens from the 12. Let's go ahead and draw the other 6. Every carbon has 2 hydrogens. So now the equatorial line. The equatorial line is opposite to the axial. It's a tilted line. So if the axial is up, then the equatorial definitely it's going to be down. Now how I represent it, it's a line along the equator like this, away from the cycle. Okay? You can simply represent it, you can show it like this if you want, but please don't show it up like that because the up is going to be the axial, and the axial is a straight and a perpendicular line. So this is going to be the equatorial. For this carbon, your axial is down, so your equatorial is going to be up. Axial up, equatorial down, and the equatorial can either be towards this side or the other side. It does not matter. For this carbon over here, axial is down, so the equatorial is going to be up. Just it looks nicer if you put the equatorial outside the cycle and not in the cycle. So don't put it in the cycle, make it outside the cycle. Here, your equatorial is going to be down, and we're going to say the same thing. Don't put your equatorial in the cycle, it's outside in there. Because if you build the molecular model, you're going to see that the equatorial is going to be outside the cycle. And then for this carbon, axial is down, so the equatorial is going to be up in this case. So as you can see, equatorials, these are lines around the equator. They are not perpendicular lines. They are opposite in direction of that of the axial. So there is no interaction between the groups in the axial position and the groups in the equatorial position in there. And then you go ahead and you fill your hydrogens in there. This is a simple representation of a cyclohexane structure that has no substituents on it. We don't use wedges and dashes when we have substituents in the cycle and we want to represent them. So if you want to draw a chair conformation in there and show a CH3 on it, please don't use the dash or the wedge in there to represent the substituents. No, we're going to use axials and equatorials. So wedges and dashes, they are not for chair conformation. You use wedges and dashes whenever you are simply having a cyclohexane, not in a chair conformation. And then if you have two substituents in there, yes, you can do that. And this is going to be trans 1,3-dimethylcyclohexane. But if I want to change this into a chair conformation, we're going to talk about it as we proceed, then please do not use the wedges and dashes to show the positions of the CH3s. Instead, we're going to go ahead and use the axials and the equatorials. Chairs undergo rotation. That rotation, we call it conformation. So as we did for the alkanes, they undergo rotation and we express their rotation by Newman projection. We're going to do the same thing for cyclohexanes. Cyclohexanes, they undergo rotation, and to express their rotation, which is the conformation, we're going to show it in a chair conformation or a chair form, and we're going to show how the chair form is being rotated. Now, the rotation of this chair form is different than the Newman. The rotation of the chair form is a flip. So the chair flips. And the way that the chair flips is simply by flipping its carbons in there. So you look at the carbon that is pointing up and you look at the carbon that is pointing down and simply you flip it. You flip the chair. So that carbon that is pointing down now becomes a carbon that is pointing up here, okay? And the carbon that is pointing up, that's represented by a green. Now we're going to bring it down and it's going to be shown in the other chair form being down. This is called a conformation, a chair conformation. So for every representation of a chair for cyclohexane, there is a chair flip. The chair flips and you can show it or express it in a different conformation. The chair forms are called conformer 1 and conformer 2. These two are different, and the difference is their rotation in space. This is why we call them conformers in there. Now, before the chair goes into its stable, flips out and goes into its second stable form, which is conformer 2, it's going to pass by a lot of intermediates in there. One of the intermediates is a boat conformation or a boat form. Now, all the intermediates that it passes by before it becomes a second conformer, all of these, they are very high in energy, and each one has a name. There's a twist boat, there's a boat. The boat has a higher energy than that of the twist boat. And all of those are unstable. The reason why? Because again, they have high energy. But we care about the chair and its conformer in there. Notice the numbering. You can number anywhere you want. But see here, carbon number one was down. So now it became up in there. Okay. I still have carbon number two in the same position, carbon number six in the same position there. And then carbon number four is up, and now it's going to be down. We're going to use the terms up and down a lot. Let's go ahead and have an example. Let's start with an easy one. And let's go ahead and consider this compound, which is a methyl cyclohexane. And let's draw the conformers of methyl cyclohexane. So draw the two conformations of methyl cyclohexane and figure out which one is more stable and determine which is more stable. So every time we're asked about a question about the stability, you have to change the cyclohexane and make it a puckered conformation so that you know exactly where the CH3 lies. Is it on the axial or the equatorial? When we have a methyl cyclohexane, here I'm not specifying the direction of the CH3. I'm not telling you here that the CH3 is up or down. So you have to consider both cases in there. So you start by drawing the chair conformation. So we're going to go ahead and draw the chair conformation. Here I'm drawing it in one drawing in there because I am used to it. Okay, so here you go. This is the chair conformation. Because it is a methyl cyclohexane, the CH3 can be on any carbon of the cycle. Any carbon of the cycle. You can start numbering anywhere on the cycle. I'm going to start numbering from here, giving this carbon number one. I can put the CH3 either on the axial position or the equatorial position. I'm going to choose to put the CH3 on the axial position. Because after I do this, I'm going to do the chair flip. And when I do the chair flip, that axial position will turn into an equatorial. So I would consider both cases. So this is the first conformation of the methyl cyclohexane. So I'm going to call this conformer A or conformer 1, whatever you want to call it in there. Now I'm going to go ahead and do a chair flip. To do a chair flip, we're just going to represent it by an arrow like this. It's normally an equilibrium arrow, but after you figure out which one of the conformers is more stable, the equilibrium is going to lie towards the more stable conformer. So it's not going to stay equilibrium like this unless two conformers have the same stability. And we're going to consider those cases as we proceed. So over here, we're going to do the chair flip. As I said, when you do the chair flip in there, locate the carbon which is up, locate the carbon which is down, and simply flip it. So flip that carbon up and flip that carbon down. And we're going to keep everything the same, but we're going to go ahead and flip the chair. Here you go. So now this is carbon number one. This was carbon number one that I care about that has the substituent. I want you to use those terms up and down, and I want you to label your substituent, please, where it is. It's on the axial. The axial is up, so it is up. By definition, when you flip the conformation, whatever is up stays up, whatever is down stays down. You are not changing the orientation of your substituent. So your substituent is going to stay in whatever orientation it is in. If it is up, it's going to stay up. And if it is down, it's going to stay down. But when you do the flip, axials always change into equatorials, and equatorials have to change into axials. So this one is an axial which is up. It's going to be equatorial and it's going to stay up on carbon number one. The equatorial position on carbon number one is pointing up over here. So this is the equatorial position because the axial position is down. So the equatorial is up. So this is why I need the CH3 to remain up, and I would need it to be on the equatorial position. So here you go in there. Okay. This is called conformer B. So the relationship between conformer A and conformer B, those two are conformations. Um, these they have different rotation of the molecule in space. So the molecule here is oriented differently in space. Conformer A is not the same as conformer B, because as you can see here, the CH3 is on the axial and then it became on the equatorial. Although it stayed up, but still it is different now. Because if you take this and put it on top of that, these are completely different structures. The difference is not in the connectivity of the atoms. The difference is in the rotation of the molecule in space. Okay, now the other question is which one is more stable? Stability has to do with energy. So the more or the higher the energy is of the structure, the less stable it is. And the energy has to do with the interaction. Interactions only happen within the axial positions, not within the equatorial. So if your group is on the equatorial position, your group will not interact with any of the groups around it because it is very far away. But if your group is on the axial position, it will, and the interaction is going to be with other groups that belong to the axial position. So here, what I have is two axial positions. I have an axial hydrogen here, which is pointing in the same plane. Since the CH3 is up, I need to look for the axials that are up. And I have two axials that are up in here. Equatorials are far away from the CH3, so there will be no interaction between the axials and equatorials. But there is always an interaction between axials and axials in there. So here what I have is a CH3 axial interaction, CH3 hydrogen axial interaction, and the CH3 hydrogen axial interaction. This is a 2 times hydrogen CH3. It's an axial interaction. The hydrogen is on carbon number 3. Whether you start numbering from this carbon going 1, 2, 3, or whether you start numbering from this carbon going 1, 2, 3 in there. So you have a 1, 3 diaxial, because you have two axial interactions. So you can call this 1, 3 diaxial interactions in there. Now, each hydrogen CH3 axial interaction is a 0.9 kilocalories per mole. So each hydrogen CH3 axial interaction is a 0.9 kilocalories per mole. And since I have two of them, so you just multiply this by 2, and this is a 1.8 kilocalories per mole. This is the energy of conformer A. Conformer B, because the CH3 it's in a different plane. It's very far away from the axial hydrogen. So I have an axial hydrogen here, which is pointed up, and I have another axial hydrogen here, which is pointed up. But it's in a different plane. There is a big difference between the plane of the axial and the plane of the equatorial. So there is no interaction between equatorials and axials in here. So the energy here is 0. There is no energy. So since there is no energy, conformer B is going to be most stable. So when I'm expressing the equilibrium now, the equilibrium is going to lie more towards conformer B and a little bit more towards conformer A. So from this example, we deduce that we want our groups to be on the equatorial position. The more, the better. Okay, let's have another example here. If I have something like this, if I have a CH3 pointing up, a CH3 pointing down, and a CH, and then let's put an ethyl group in there, pointing up. And the question is, draw both chair conformations of this substituted cycloalkane and determine which is more stable. Now, in this case, you're going to go ahead. We don't care where to position the group. So you're going to go ahead and position those groups, do a chair flip, and then choose the compound that has more substituents on the equatorial position rather than the axial position, and make that more stable. So we're going to start by drawing the chair conformation. As I said, to draw the chair conformation of substituted cycloalkanes, please label your substituents in there, which direction they are in. So this CH3 is up, this one is down, and this one is up. The ethyl is up. We want to keep them in the same position every time we draw the chair conformation. So, and you can number anywhere you want in the cycle. So I'm going to start numbering from here. It's going to be 1, it's going to be 2, and this is going to be 4. And I'm going to start numbering from here. It's going to be 1, this is going to be 2, this is going to be 3, and that is going to be 4. So on carbon number 1, I do have my CH3 pointing up. I'm going to keep it up, and it will be on the axial position. On carbon number 2, my CH3 is down, and I'm going to keep it down, so it's going to be on the axial position. And on carbon number 4, my ethyl group is going to be up, so I'm just going to go ahead and keep it up, and it's going to be on the equatorial position, because the equatorial position is up and the axial position is going to be down. Now I'm going to go ahead and do a chair flip. So let's draw the equilibrium arrow first. Doing the chair flip, we're going to take this carbon and flip it. So we're going to move it this way, and we're going to take this carbon over here, and we're going to move it in the other direction. So you're going to end up having your chair flip. We're going to keep the same numbering in there. This is the whole idea. So now carbon number 1 is here, and carbon number 4 is here. On carbon number 1, the CH3 is up. It's going to stay up. So it's going to stay up. Now it's going to turn into equatorials. Remember what I said, that axials turn into equatorials, equatorials turn into axials, but the orientation of the car CH3 stays the same, or the position of the CH3 stays the same in there. For the second carbon, now for the numbering, I can go by simple 1, 2 here or 1, 2 there. It doesn't matter. I'm just going to stick to the to carbon number 2 being here. And the CH3 is down, so it's going to remain down. And down is on the equatorial. And it always makes sense because axials turn into equatorials in there. And then on 4, I have my ethyl to be down, to be up. Sorry, this one is up there, because the down is the axial. So this one is up, it's going to stay up. So now it's going to be on the axial position. And I have here 2 carbons in there. I can simply draw it in a skeletal form, or I can do CH2, CH3 in there, whatever you want. So here you go. So you got, this is what you got. Let's go ahead and label our substituents. So on carbon number 1, I have an axial. On carbon number 2, I have an axial. And on carbon number 4, I have an equatorial. Here, on carbon number 1, I have an equatorial. On carbon number 2, I have an equatorial. And on carbon number 3 or 4, I have an axial. So notice here, I have 2 groups that are equatorial, 1 group that is axial. Here, I have 1 group that is equatorial, 2 groups that are axials. So I'm just going to go ahead and go with the more equatorials, more stable. If you want to get the energy of this structure in here, see what interactions do you have. The CH3 that is up, it's going to come and interact with all the axial hydrogens that are up. So let's label those hydrogens in here. You have an axial hydrogen up here and an axial hydrogen up here. So you're going to have 2, 1, 3 diaxial interactions in there between the CH3s and the hydrogens. And the CH3, which is an axial down, it's going to come and interact with the CH3s that are axial and they are in the same plane as the CH3 that is down, which are these two hydrogens in there. So you have four hydrogen CH3 diaxial interactions, two up and two down. This is going to increase the energy of the structure and make it more energy, less stable. Now, this ethyl group, because it's on the equatorial position, it's far away from all the interactions, so it's not going to interact with any. So here I do have four hydrogen CH3 axial interactions. Okay, here on the other end, I'm gonna end up having an ethyl group on the axial, and that ethyl group is going to interact with all the hydrogens that are up because the ethyl is up. So I have a hydrogen here which is up, and I have a hydrogen on the axial here which is up. So I'm going to end up also having a 1,3 diaxial interaction in there. But that diaxial interaction is going to end up having less energy than the four diaxial interactions that I have in the other structure in the other conformer. So this one is going to be more stable, and when I want to express the equilibrium arrow, it's going to be more towards conformer B and less towards conformer A. So this one is the one that is more stable, and this one is the one that exists at equilibrium. Now, let's say if we have bulky groups. Bulky groups are branched alkane chains. These bulky groups, they have a lot of energy when they do the diaxial interactions. So this is why bulky groups, we do not prefer to put them on the axial position. So when you're working with stability question and you have a bulky group as one of your substituents in there, that bulky group will always prefer to be on the equatorial position rather than the axial position. Something similar to the tertiary butyl group. This one should never be on the axial position. It should be on the equatorial position. Reason why? Because if you have it on the axial position, you're going to end up having your diaxial interactions. Now, this is not a regular CH3. So the diaxial interactions here, see how much they are? It's like a very high number in there. It's a 21. The unit that I'm using here in this table is kilojoules per mole, not kilocalories as in the example before. But the value of the energy is really high in here. And because it is high, see there's a difference in the energy between a CH3 and a tertiary butyl and an isopropyl group. This is an isopropyl group. So isopropyl groups, they always prefer to be on the equatorial position. Tertiary butyl groups, they always prefer to be on the equatorial position. These are branched alkanes, and we always want them to be on the equatorial position. So no matter how many substituents you have on your cycle, always make sure that these two are always on the equatorial position and not the axial position. So the direction of equilibrium is always towards the conformer that has those bulky groups on the equatorial position. Let's have an example in there. Okay, so we did that. Let's have an example. So let's draw all conformations, and you have more practice of these in the extra problems. So please do your practice. Let's say, for example, if I gave you 1,3 dimethyl. Let's keep it 1,4. So let's have 1,4 dimethyl cyclohexane. And I want you to draw the chair conformations. So draw all chair conformations. And then determine which is more stable in there. Now, since I have a disubstituted cyclohexane, when we talked about disubstituted cyclohexane, we said that, or cycle in general, we said that when you have two substituents, the substituents can either be on the same side, okay, or they can be on opposite sides. Because I did not specify here, I said 1, 4. So these substituents can either be on the same side or they can be on opposite sides in there. And if they are on the same side, we're going to call this a cis isomer. And if they are on opposite side, we're going to call it a trans isomer. Now see here, I'm using the wedge and the dash because I am representing the cyclohexane in a planar structure. I want you to draw this before you change this into a chair conformation, just to know the location of your groups on the cycle, where they are, and what is their orientation. Here, I could have placed the two CH3s down, both of them, but it's going to be the same. So I'm just going to go ahead and choose the CH3s being up. Because if I choose the up and do the chair flip, they're going to be down anyways. Um, here I could have written the CH3s and of being down instead of up. I could have shown the CH3s here down instead of up, and there's still going to be cis, both of them, but it's going to be the same. So just pick one. Let's go ahead and start with the cis, and then we're going to go to the trans. So let's start with the cis isomer. Remember, the cis and the trans, these are geometrical isomers. There is no rotation between cis and trans. You cannot rotate cis and get a trans. We said this before. Cis and trans are completely different compounds. They are stereoisomers because they differ by rotation. They do not differ by connectivity. They differ by rotation. So this is why we call them stereoisomers in there. And the type of the stereoisomers is a geometrical stereoisomers. So let's start with the cis isomer. We're going to change that into a chair conformation. As we did before, we're going to locate where the CH3 is. This is up, this is up. So this is on carbon number 1, this is on carbon number 4. Let's go ahead and label our carbons. I'm going to make this one carbon number 1 and this one carbon number 4. I need my CH3 to be up on carbon number 1. So I'm going to make it up, which is the axial position. And I need it to be up on the carbon number 4. So it's going to be on the equatorial position. Let's do the chair flip in there. Okay, start with the equilibrium arrow. And when we do the chair flip, now this is carbon number 4, and this is carbon number 1. If the CH3 is up, it's going to remain up. So now it's going to be on the equatorial position, which is something good. And on 4, the CH3 up is going to remain up, and it's going to turn into an axial position. Notice here that I have similar percentages of axials and equatorials because I have one group which is on the axial, the other one is on the equatorial. And here I have one group which is on the equatorial because axials here turn into equatorials. So this one is going to be on the equatorial and the other one is on the axial. So I have a 50-50% chance. So I would say that these two, they have the same stability because both they contain 50% axial, 50% equatorial. There is no conformer that has more equatorials than the other. So this one is 50% axials, this one is 50% equatorial, and then 50% equatorial, 50% axial in there. So these one have the same stability, so I'm just going to go ahead and keep the equilibrium arrow, and this is the equilibrium arrow for the two conformations. There is no conformer that is more stable than the other. Let's go ahead and do the trans. So for the trans, I do have this CH3 pointed down and the CH3 pointed up. So we're going to go ahead and change that into a chair conformation. On carbon number 1, my CH3 is pointed down. I'm just going to label this one as carbon number 1, this one as carbon number 4. And on carbon number 4, my CH3 is labeled, or it's up. So here you go, it is up. Notice here, my groups are what? My groups are both, they are on the equatorial position. So this is extremely stable in there. Those CH3s, they will never interact with the axial hydrogens. So if I have an axial hydrogen down here, those two CH3s or those two hydrogens will not interact with the CH3. And if I have axial hydrogens up, those two hydrogens will not interact with the CH3 that is up. So because they are in different planes. The plane here is different than the plane of the CH3. So let's go ahead and do the chair flip. And doing the chair flip in there, here you go. So that's carbon 1, that is carbon 4, this is carbon 1, and this is carbon number 4. The CH3 is down. It's going to remain down. Now it's going to become on the axial position. And the CH3 on carbon number 4 is up. It's going to stay up. So it's going to be on the axial position as well. So I'm going from equatorial to two axials in there. This is extremely unstable. Unstable because what? Because I do have the 1,3 diaxial interactions in there. So the CH3 that is up is going to interact with the axial hydrogens that are up. So I'm going to end up having the 1,3 diaxial interactions in the plane that is up. And then for the CH3 that is down, I'm going to end up having that CH3 interacting with the axial hydrogens that are down. So I'm going to end up having 4 times 1, 3 diaxial interactions between the hydrogen and the CH3. Of course, the table that I showed you earlier, you're not responsible to know these numbers by heart. You will have those values in the exam. So in this case, that is going to increase the energy of the structure, make it less stable. So your equilibrium arrow now is going to be towards the equatorial and not the axial. So please change that. And it's the equatorial conformer that exists. It's the equatorial conformer that exists more than the axial in there, and this is one is going to be more stable. So back to our question, which one of these chair conformations is more stable? Is it the cis or the trans? To locate the stable one, you need to have one conformer from them to be very stable. The trans has both substituents on the equatorial position. The cis has same stability of conformers. So definitely now the trans is going to be more stable than the cis.